So we're going to dig down, because these kind of false positives where it looks like they have it and they don't is very common. It's very common. And there are a couple of reasons why I'm going to dig into this. One is there's this gap. Kids come with a lot of knowledge, even in elementary school, but in high school and whatever. They come with a lot of informal familiarity with fractions, with decimals, with whole numbers. But there's a big gap. And the research is really fun in this area, because you see, my favorite is the study they did with shoppers, grocery shoppers in Orange County, California. So these are people, and they were studying these grocery shoppers in the wilds, in their natural setting of Safeway and places like that, and looking at the math that they did when they were comparing items about what to buy. And then they gave those people the same math problems in a school format, and they couldn't do it. So it was totally disconnected what they'd learned in school from the skills they had managed to acquire to survive in the wilds of Whole Foods. So, and they find this with Brazilian street vendors, people who had no education, who are doing complicated math. They're selling to tourists and figuring stuff out, and they've had no learning. And so we develop ways to do math in the natural world. We have all this informal knowledge, and it does not connect often to what's in school. So kids look like they can do stuff, but maybe what do they really have? And when we teach them a procedure without understanding, there's no fluidity. I know what to do. I know the procedure when the denominators are the same. When they're not the same, I go to whole number strategies, because I don't know what to do. So because I don't understand it, I've just learned what to do. When I see it in a way that isn't familiar, I can't be fluid with it. I can't go with the flow. So how do we know fractions? How do we learn fractions? I'm going to talk about three areas. One is that there may actually be an innate fraction sense. As part of our number sense, there may actually be a fraction component to it. There's informal experiences and then formal learning. So we are born to do math. You're laughing. I don't get it. We are born. It's my picture. Why, do you recognize that person? I do. I had one of them. He looked just like that, too, when he was that age. We are born to do math. We can subitize. People know what subitization is. The ability to recognize a quantity without counting. So you flash dots up on a screen, and you know that's 3. You don't have to count. They do this with infants. It's interesting. I'll show you a picture of what they do to poor kids. But humans are able to subitize as infants to recognize quantity up to 3 or 4. You flash dots, I know that that's 3, I know that that's 4, I know it's 2, I know it's 1. We're almost as good as chimps. Chimps can do up to 6. If you go to Google and type in subitize or subitizing, one of the links will come up as a BBC thing. You can actually do a little game and compete against the chimps. So it's kind of fun. This thing flashes up. There's seconds are counting. It wasn't taking me 13 seconds to know that this was 3 dots. All right, I'm just telling you. But I was taking a snapshot of it to share with you. So I'm better than that. But we're able to do that, which isn't surprising, because when you can play this great game about evolutionary psychology to explain why these innate behaviors exist. But it's not like anybody left a diary from 100,000 years ago or 5,000 years ago about how I could do these things. Why it's a survival value to recognize, are there 1 or 2? Are we even? How many do I need? How much do I need to feed my litter? We're able to compare as infants. We're able to tell, and most animals they've ever tested are able to tell the difference between a lot and a few. There's 80 and there's 20. Should I stay and fight or should I run away? Those kind of comparisons, we're born with that ability. We're mathematicians. We can do that. And there's a great study they did with, I think, 6th graders. And they had a little activity where people tell which is more, yellow or blue? Quick look, that's it. You got to tell at a glance. And you can't count. So they have this thing where it flashes, which one's bigger. And it's easy when there are a lot of one and not very many of another. When the ratio of the the things you're comparing gets closer to 1 to 1, it's harder. And people who are good, who are better at distinguishing which is more when the ratio is close to 1 to 1, are highly correlated to being successful in math throughout their academic careers. So they tested kids in 6th grade and then looked back, and then they tracked them forward. And kids who were good at doing this, and this is like the people who are good at going to the grocery store and judging which line to get in. Right? It's the same skill. That's a life skill. And it is highly correlated to academic success in math through K-12, throughout your academic career. And it's a great question. They're looking at, is it actually a cause and effect? Is there some spatial ability that's represented by that kind of comparison that's actually part of making you good at math? So we're able to do that at birth. So we're born to do this. We're able to add and subtract. So this is the kind of stuff they do to these poor little kids. This kid with a binky and all these wires on his head. And there's 2 little dolls back here, and they do this. They watch for surprise. They habituate somebody so a kid is like bored, and they're looking, okay, 2 dolls, yeah. So what else? And then they'll show 1, and they're like, wait a minute, there were 2 there. And they'll know, they're able to, doing these incremental studies, they're able to say that infants can add and subtract up to 3. So it's like, wow, that's pretty good. We got a lot of talent we're born with. We got a good starting base. We may even be able to recognize fractions and ratios. So they've done some studies. They've just started. And they started by kids taking a book or an object on the edge of a table. And the little kids are like, okay. And then when the book gets too far over the edge, like it's going to fall, and it doesn't fall, they're going like, hey, wait a minute, that's supposed to fall. And it's probably this exploration that kids are doing and why you end up cleaning up so much is they're pushing everything to the edge until it falls over. They're exploring some ratio concept, some proportional concept. But this, again, it's this sort of comparison, and they've done these studies, again, where they habituate somebody with a ratio, and that kids notice the difference. Again, the greater the difference, the easier it is to notice, but they seem to recognize this difference. And there was a study recently, this is all very new, so this is a study from earlier this month, notation-independent representation of fractions in the human parietal cortex. It's great stuff. You got to be careful. This is, I don't know if you follow like Science Daily, or you'll see these things in the ASCD news briefs or whatever, and it's like, oh yes, we've now found out that fractions, we all have this innate ability to represent fractions, and it's processed in the same part of the brain that whole number quantity is in the interparietal sulcus. And now we have, now we know how to teach fractions. This was a study with 12 right-handed German adults. So I'm not ready to make a big proclamation about this, but it is interesting because what they found is whether fractions are represented as a number or written out, the processing was the same part of the brain lit up, and it's the same part of the brain that lights up when people process whole number quantity. So maybe there is a common representation of quantity, and that we use that, and it is, we see 3/4 and numbers close to 3/4 quickly and differently than we see ones when we compare 3/4 to 11/22. And so they did all these different studies and stuff, and it's kind of like, it's very interesting that we do have these parts of the brain that seem to be dedicated to mathematical thinking and spatial awareness, and that relates to fractions as well as whole numbers. But we're still, this stuff is early, and don't jump off, don't say, well, we're going to do it now because of those 12 right-handed Germans.